Alright, now that this course is wrapping up, I received a study guide to review for the final exam, and I don't know. I guess the best way to study would probably be to just compile all the information into one place and then go through it. And I mean, while making a video might not be the most useful thing for you, just because it's like just a more or less a combination of just like a whole bunch of stuff material that's already been covered on the other videos and lectures and stuff. Maybe this could be useful as like some sort of overview, or maybe to help like remind, or as a reminder of some of the like real important parts of this series. And if not, then I mean, at the very least, it's a helpful tool for me to study. So we're going to start this, and we're going to go over some topics in ring theory, representation theory, and group theory. Now, the representation theory video might actually be useful because I didn't actually go over it in any of those lectures. So that might be useful. But this ring theory stuff, this is the basically, I think pretty much everything that's in here has been covered before. But I typed it all up really nicely and everything, so let's just go through it. So we start with prime avoidance, and we sort of have two types of prime avoidance. In one of them, you suppose that you have an ideal contained in a union of prime ideals, and in the other scenario, you have an intersection of ideals contained in a prime ideal. So let's do the first one. If you have an ideal which is contained in a union of prime ideals, then that ideal must be contained in one particular prime ideal, one of the prime ideals that was part of the union. And to prove this, we actually look at the contrapositive. So you suppose that A is not contained in P for every single prime ideal P in this union, then if it's the case that A is not contained in every single PI here, then A is not going to be contained in this union. Or equivalently, there will be an element which is in this union but not in A, i.e. there is an element A which is in fancy A but not in the union. Oh, I may have mixed that up. So you have an A which is in A but not in this union. That's what it means to be not included in here. Alright, so now for the case of n equals 1 is obvious. If A is not contained in P1, then there is some element which is in A but not in P1, and that's exactly what we want. So now we have to do induction. So suppose that the claim holds for some natural number n. Again, this doesn't include 0. Let I, just to make writing easier, let I be the indices from 1 to n plus 1. Suppose that Pi is a collection of prime ideals, and we've got n plus 1 of them, and A is not contained in any of these prime ideals. Now for each index, we can choose some element AI which is in A but not in the union of the other ones because of our induction our induction hypothesis. Because this union here, this union is taken over n many prime ideals, and the induction, we're assuming for the induction step that the claim holds for n, meaning that if A is not contained in if A is not contained in Pj for all j and I, then in particular, if you fix an I, A is not contained in Pj for every index j which is not equal to this lowercase I, and so then that means that there is some element A which is in the ideal A set minus the union of the ideals corresponding to indices which are not that particular lowercase I. Alright, so we have AI is in A, but it's not in the union of the PJs where j is not equal to I. So now, if there is some I such that AI is not in PI, then we're done, because then AI is in A, but it's not in, well, not only is it not in the union of the PI, of the PJs where j is not equal to I, then it's also not in PI for that particular I, and so it's not in this union. and that's the desired outcome that we want. Now assume for a contradiction that this doesn't hold for any of the AIs. Now we're going to construct an element A, which is you take the product of A1 through AN, and then you add AN plus 1. Now if it happens to be, A is either going to be in PJ, well, okay, so where can A be? Let's see here. So suppose that A is in PJ for some j less, which is strictly less than n plus 1. Then, in this case, we can write an plus 1 as A minus this thing, and since this is a difference of things in PJ, this is in PJ, which is impossible. Why is this product in PJ? This is because, so if j is less than n plus 1, oh, do we have to do this case of j equals 2 separately here? Let me think about this. No, we don't. Because j is strictly less than n plus 1. So aj appears in this product here. And we know that aj is in A, but it's not in the union of all the other PIs. Wait, so then why is this in PJ? Why is this in PJ? Oh, yeah, because AJ is in PJ for all I. We're assuming that for contradiction. So j is strictly less than n plus 1, so AJ appears in this product, and so this product contains AJ as a factor, and since AJ is in PJ, and since PJ is an ideal, this entire product is in PJ, and we've just assumed here that A is in PJ. So this difference is in PJ, and so AN plus 1 is in PJ, which is impossible since we chose AN plus 1 to not be in PJ for any j strictly less than n plus 1. In particular, AN plus 1 is not in this particular PJ. So assume instead that A is in Pn plus 1. Then you look at the product from A1 through AN. Well, this can be written as A minus AN plus 1. And AN plus 1 is in Pn plus 1, and A we're assuming here is in Pn plus 1, so this thing is in Pn plus 1. So since Pn plus 1 is prime, some factor here must be in Pn plus 1, i.e. there is some I less than or equal to n such that AI is in Pn plus 1, but that's impossible since each AI is chosen to not be in Pn plus 1 since n plus 1 is an index which is not equal to this I when I is strictly less than n plus 1. Alright, so let's see here. So A cannot be contained in any particular PI, and why is that a contradiction? Alright, I was able to fix this, and I fixed it because I wrote it down incorrectly. As desired. Yeah, sorry. There's a special kind of frustration that comes with algebra that doesn't really come with other types of math that I find more interesting. And yeah, I don't know, but I had to go back and relook at this problem from when I did this previously, and I realized that I had written it down wrong, and there's my logic wasn't quite I didn't follow the same line of logic as before. The conclusion, you don't want to prove that there must be some AI which is not. You don't want to prove that AI, that there has to be some I such that AI is not in PI. So that's even, I mean, that, it might be true. I mean, I don't know. This is so, like, now this doesn't really, this argument doesn't really tell you anything about, like, is this true, is this not true? I don't know, maybe you would go explore it if you like, find rings useful for anything. But, so suppose that AI is in, So you suppose it is the case that AI is in PI for every single I and I, and like this could while we don't know for sure if this is a scenario that will ever actually happen, we know that it's we're going to be able to get what we want despite this being true. So what you do is you let A be this element, and like I've discussed, A is not in PJ for, so A is not in PI for any I between 1 and n plus 1, because we did one argument to prove that it's not in PJ for any j strictly less than n plus 1, and we also proved that it's not in Pn plus 1. So therefore, you have an element A which is not in the union from 1 to n plus 1 of the PIs, but because each AI is in A, obviously, then this element A will be in this ideal A. So A is in this set, which is exactly what we want to prove. We want to conclude that there's some element in this set. So either we're going to get this element automatically by finding some I such that AI is not in PI, or if we don't know that AI is not in PI for some I, then you can use the fact that AI is in PI for all I to construct an element which necessarily is not in this set. And that completes the proof. That's all you need. So that's that. Just okay, so we finally finished the first of many things that we need to prove here. So next part, prime avoidance part 2, similar but different. Easier. So if you have ideals which are contained in A, and P is a prime ideal, then if the intersection of the AIs is contained in P, we want to prove that AJ must be in P for some J, and furthermore, if this intersection is equal to P, then there's some J such that AJ is equal to P. So again, just like in the last proof, we're going to use the contrapositive. So suppose AJ is not contained in P for every single J, we want to prove that this intersection is not contained in P. So suppose AI is contained in this AI set minus P for every single I. So yeah, if for every single, I don't know why I switched from J to I here, whatever. So if AJ is not contained in P for every single J, then you can find an element which is in AJ but not in P. So that's how we find these AIs. Now let A just be the product here. We don't have to do any like product and then sum or whatever. Then A is contained in this intersection because for every single ideal AI, the element AI it appears here is in that ideal, and it's just being multiplied by a whole bunch of stuff, which, since this is an ideal, keeps you in the ideal. So for every single ideal AI, A is in AI, and so A is in the intersection of the AIs. But we also know that A is not in P, because if A is in P, then since P is prime, some factor AI must be contained in P, but that contradicts our choice of AI for every single I. So therefore we have an element A which is in this intersection but not in P, i.e. this intersection is not contained in P, and that's the exact contrapositive statement we wanted to prove. So now if this intersection is equal to P, then in particular it's contained in P, and so we know that there is some J such that AJ is contained in P, and so then you have P is equal to this intersection, which is obviously contained in any particular AJ, and so you have AJ equal to P because you have inclusion in both directions, and you're done. Coffee. Maybe coffee will save me from this test. We shall see. So we have the equivalent definitions of Noetherianity. So we have the ascending chain condition. We have that every non-empty set of ideals has a maximal element, and that every ideal is finitely generated. To prove A implies B, suppose you have some start with any ideal in S. If this ideal A naught is maximal, we're done. Otherwise, there's some A1 such that A0 is properly contained in A1. Because if no such A1 existed, then A0 would be maximal. Then, again, if A1 is maximal, we're done. Otherwise, there exists some A2 such that A1 is properly contained in A2. And continue this process until we arrive at some natural number n such that an is maximal. Assume for contradiction that no n exists, then that means this, considering A0 contained in A1, ... is an ascending chain which never terminates, which contradicts the ascending chain condition, and thus if the ascending chain condition holds, then every non-empty set of ideals S of A has a maximal element, and we're done. Okay, now for B implies C, suppose A is an ideal, and we want to prove that it's finitely generated. So let S be the set of finitely generated ideals which are contained in A. If we can prove that it has a maximal element, and prove that that maximal element is A, then A must be finitely generated. Okay, so S is non-empty since it contains 0, the 0 ideal. So by B, S has a maximal element, let's call it M. Now assume for contradiction that M is not equal to A. Then there is some element A which is in A but not in M, and then the ideal generated by the ideal M and the element A, well, since M is finitely generated, since it's in S, adding in one more generator will still make it finitely generated. So it's finitely generated, it's contained in A, and so it's in S, but it also properly contains M because it contains an element which is not in M, and that contradicts the fact that M is maximal. And therefore, M must be equal to A, and thus A is finitely generated. And this holds for every ideal in A, and thus every ideal in A is finitely generated. Okay, so now we want every ideal being finitely generated to allow us to conclude Noetherianity. So assume C and let A0, A1 be an ascending chain. Let A be the union of these things. We want to prove that's an ideal. Because we want to, prove it's an ideal. So to prove it's an ideal, obviously 0 is in there. If you have two elements, A, B, and A, then you have indices I and J. Assume without loss of generality that I is less than or equal to J. We'll say A is an AI and B is an AJ, and then A plus B. Well, since A is an AJ as well, this sum is an AJ since AJ is an ideal, and that's going to be contained in A. And then for any R, RA is an AI, which is an A. So therefore it's an ideal. So now it's finitely generated, say by elements A1 through AN. So each AI is contained in some ideal AMI, where the MI is an index depending on I. Let n be the maximum of these indices. Then if you choose any index m greater than or equal to this capital N, AM must be contained in A because of the definition of A. However, since AM contains all generators of A, why does it contain all generators? Because AMI is contained in every AJ for J greater than or equal to MI. And so, for every single AJ where J is greater than or equal to capital N, it will contain all of these generators, all the AIs. So, since AM contains all generators, A is contained in AM, so they're equal. So, AM equals A capital N, which equals the ideal A for every single M greater than or equal to N, and so this ascending chain terminates, and this holds for every single ascending chain, and thus the ascending chain condition holds. And we're done. So A implies B implies C implies A, which means they're equivalent. Alright. Hilbert basis theorem. Let A be Noetherian. Prove that the polynomial ring AX is as well. This is weird because you have to talk about not only rings but also modules. Alright, so we want to prove that every ideal of A of this polynomial ring is finitely generated. So let B be an ideal in this polynomial ring, and we want to prove it's finitely generated. So given any polynomial f in the polynomial ring, define h of f to be the highest order coefficient or leading coefficient, whatever. So if f is identically 0, then h of f is equal to 0, and otherwise if f can be written as the sum of a I x the I, where the highest power here an is not equal to 0, then we define h of f to be an. Now let p be the all the leading coefficients of polynomials in B. I claim it's an ideal. Certainly it contains 0. If you have two elements A and B in P, then you have corresponding polynomials f and g. Write them in this way. So, and the leading term of f will be an, which is a, and the leading term of g will be b. Without loss of generality, we can take n to be less than or equal to m. Since b is an ideal, we can multiply by a polynomial to stay in the ideal. And in particular, we can multiply by the polynomial x to the power of m minus n. Remember, m is greater than or equal to n, so this works. So if you take these two things, add them together, you stay in the ideal. And their leading term, well, the highest order term will be, well, you had a here, and by multiplying by x to the m minus n, the corresponding power of x will be increased up to m. And so the highest power, this polynomial will have degree m and leading coefficient a. This one will have degree m and leading coefficient b. So the leading coefficient of the sum of these things is a plus b, so it's in there. Also, if you have any element in the ring, then it's a constant polynomial in the polynomial ring. So Rf is in B, and its leading coefficient will obviously be R times A. And so it's closed under multiplication, and therefore it's an ideal. And by Noetherianity, it's finitely generated by P1 through Pn. So these P1s through Pns, these are all elements in the ring. So for each I, there's some polynomial Fi in B, the ideal B, such that the leading order of the leading power of Fi is equal to this Pi. Alright, so what we're going to want to do is we're going to want to use these Fi's to sort of cancel out any higher order terms that we get, any like higher power coefficients. But in order to do that, you need to have large enough degrees to sort of play with. So you need to figure out something to deal with polynomials of lower degrees, and that's where you talk about modules. So let D be the maximum degree of these Fi's, and let M be the A module generated by the polynomials of degree 1 through x to the d minus 1. Right. M is finitely generated, and A is Noetherian, so M is a Noetherian A module. That's one of the things that we proved when discussing Noetherian modules. Also, B is an ideal, and so B is also an A. It's a polynomial ring submodule of the polynomial ring, because you can just give it like the natural action. The module action here is just multiplication in the ring, and this works out. And we've talked about that. In particular, so if it has an AX module structure, then it has an A module structure as well. And this is important because up here we consider the A module generated by these things, not the A adjoint X module. So now we have B. This should be fancy B again. Fancy B and M as A modules. And so this intersection is an intersection of submodules, and thus it is a submodule. So therefore, by Noetherianity, it's finitely generated, say, by elements G1 through Gm. So the Pi's are in the ring, the Fi's are in the polynomial, and the Gi's are in the polynomial ring as well, but they have degree less than or equal to d minus 1. Alright, so finally, let A be the ideal in the polynomial ring, which is generated by the Fi's and the Gi's. I claim that B is A. So certainly A is contained in B, since each element in the generating set for A belongs to B. For the reverse inclusion, suppose you have a polynomial f in B. If its degree is less than d, then it's in B intersect M, which is the ideal generated by G1 through Gm. Well, this generating set is a subset of the generating set for A, so this is contained in A. So F is in A. Otherwise, suppose the degree of F is, we'll call it dF. Say it's greater than or equal to d. Let A be the leading term of F. What we want to do is we want to we want to add a polynomial to f to get rid of the highest degree coefficient. So a is in p because it's the leading term of an element of b. So we can write it as a sum of, we'll say, a1 comma I pi, where each a1 comma I is in a. So for each I, let d1i be df minus the degree of fi. And then what we can do is we can write this thing, which is a linear combination of elements in B. So this is f minus the sum of these coefficients here, and we replace the pi's here with fi times x to the d1i. And what this does is this ensures that this thing here is a polynomial whose highest order term has its highest order term is precisely, well, what will it be? Its degree will be, well, fi will have degree fi, and multiplying it by something of, x to the power of df minus degree of fi will give you something of degree df. So each of these will have highest order, each of these will be of degree df, and if you take the linear combination, you'll get a. And so when you take this difference, its leading the degree df coefficient of this polynomial is going to be this difference, which is precisely 0, and so therefore the degree of this polynomial is strictly less than df. And we can continue this process until you get a polynomial, we'll call it g. So you subtract this sum, then you do the same process again to subtract a different sum, and then you keep going. Let's say you do it k times, and you get a polynomial which has degree strictly less than d. And eventually you'll get to this point because f started with some finite degree, and every time you do this process, you decrease the degree by at least 1. So eventually you'll get it to be less than d. G is in B for the same reason that every single one of these things is in B. And since its degree is less than d, it's in M as well. So it's in the intersection of B and M, which is contained in A, as we know. So we can write f as g plus every single one of these sums, and then this element will be contained in A, and therefore f is in A. So regardless of the degree of f, we can prove that f is in A, therefore b is contained in A, and so b is equal to A, and so A is finitely generated, implies that b is. And so every single ideal in the polynomial ring is finitely generated, and thus the polynomial ring is Noetherian, as desired, and we are done. Whew. Alright, here's another new thing, I guess. Artinian domains. So let A be an Artinian domain, i.e. a domain in which every single descending chain stabilizes. So it's like Noetherian, but replace ascending with descending. Prove that A is a field. So Artinian and domain means field. The statement is stupid if A is 0, because if it's 0, then, well, if A is 0, we don't even talk about the 0 ring. We don't consider the 0 ring to be a ring. So choose some element x which is in the ring but which is non-zero. Will 1 work? I don't know. I don't think 1 will work. Well, maybe. No, it'll work. Oh, yeah, of course it'll work. Because what we want to do is we want to choose some non-zero element and prove that it has an inverse. Does 1 have an inverse? Maybe. I'll leave that one for you. So, you choose a non-zero element in A and consider the chain X contained in the ideal generated by X. Well, this contains the ideal generated by X squared, because anything in this ring will be some coefficient in A times X squared, which is just whatever that coefficient was times X, that whole thing times X, so it's going to be in here. And obviously this will give you a descending chain. So by Artinianity, this chain stabilizes, i.e. there's some k such that for all n greater than or equal to k, x, the ideal generated by x to the n, is the same as the ideal generated by x to the k. In particular, x to the k is an element of the ideal generated by x to the k plus 1, meaning that there is some y in A such that we can write x to the k as y times x to the k plus 1. So now we subtract this to the other side and factor out an x to the k, and we get x to the k times 1 minus x to the y. Well, okay, well I guess I did this a more natural way. So if you look at this weird thing, well, if you multiply this out, this is x to the k minus y x to the k plus 1, and this is 0 because of this. Now since A is a domain, and since x is not equal to 0, x to the k cannot be equal to 0, because you can't multiply non-zero things together and get 0 in a domain. So therefore, the fact that x to the k times 1 minus xy equals 0 implies that 1 minus xy must be 0, i.e. x times y equals 1. So therefore, x is a multiplicative inverse given by y. This holds for every x in this ring, and so A is a field. And that's that. Alright, next thing, Euclidean domains are PIDs. Alright, so remember, what's a Euclidean domain? It's a domain with a function delta for distance, or like a norm. I wish it was a norm. Norms are nice. I like norms. I miss norms. Such that for every single A and B in this, every single non-zero element A and B, there is some Q and R in the ring, such that we can basically divide by, basically for any given A and B, we can take A and divide it by B with remainder. I.e., you can write A as some multiple of B plus some remainder R, where the size of where either the size of the remainder is less than the size of the thing you're dividing by, or the remainder is 0. And the theorem is that any Euclidean domain is a PID. So let's start with the Euclidean domain A. Certainly, the ring itself is a principal ideal. So let A be any proper ideal. Choose an element B, which is a non-zero element of A, and choose it such that this minimizes the value of delta over the non-zero elements of A. Why are we able to do this? Well, this is because the range of delta is discrete. So you can basically start at 1. No, you can start at 0 and be like, oh, is there a non-zero element which maps to 0? If so, you'd find one and choose it. If not, you'd move on to 1. And then you choose that and that and that. The only time something like this would not be possible would be if this range that you're considering were like the rationals or the reals, something where you can have a something where what's the word for this? Like for every single element there is a next thing in it. Yeah. Like the number 1 has a unique thing, i.e. the number 2, which is the next thing in the next thing with respect to ordering. Whereas given any 2 real numbers, there's a number between them, so there's not like a next one. This is a very fundamental, very basic, very easy notion in math, and it's very important, and so it's really embarrassing that I'm blanking on it, but you should know what I mean, I guess. But yeah, it feels very like first chapter of Baby Rudin type, or first chapter of Munkers or Moncries or whatever, something like that. Anyways, so I claim that A is generated by the ideal generated by the element B. Certainly, this generated ideal is contained in A, since B is in A. Now, for the reversing inclusion, well, certainly 0. What? Whatever. Okay, so 0 is going to be in B. And now, okay, so we want to prove that A is contained in B. So the first thing, 0 is in A, and that's obviously going to be in the ideal generated by B. So now suppose you have some element A which is in the ideal A but not 0. Use the Euclidean algorithm to write A as BQ plus R, where Q and R are elements in A, and so by the Euclidean algorithm, either delta R is strictly less than delta B or R equals 0. If we assume for contradiction that R is not 0, then delta R must be less than delta B, which contradicts what? Delta R is less than delta B. So by minimality of this thing, so this is where C was chosen over the elements in the ideal. So that means that R is not in the ideal A. So if R is not in the ideal A, then A minus BQ, so just rewriting this, we get A minus, well, not rewriting this, rewriting this, A minus BQ equals R. Well, R is not in A, so this difference is not in A. A and B are both in A, but that means that A minus BQ must be in A, so we have a contradiction. Therefore, it can't be the case that R is non-zero, so R is 0. Therefore, A is equal to BQ because R is 0. And this obviously is an element of the ideal generated by B. Therefore, A is contained in this ideal, and so they're equal. And so, blah, blah, blah. So every ideal of A is a PID, and so Euclidean domains are PIDs. And so that's that. Alright, let's talk about quotients and their denominators. So these are 3 facts that are very easy to prove and very easy to state. They're if and only if statements, and they're really important. So an ideal P is prime if and only if the quotient of the ring R by the ideal P is a domain. And these are basically the same thing. So P is prime if and only if whenever you have 2 elements whose product is in P, either A is in P or B is in P. Now let's rewrite this using the equivalence relation of cosets of P. So A, B, and P means the same thing as AB being congruent to 0 mod P. And this implies that either A equals 0 mod P or B equals 0 mod P. So now if this is using writing things as elements of R. Now if we move this into the language that we would use in the quotient space, it would say the A quotient times the B quotient equals 0 implies that the A quotient equals 0 or the B quotient equals 0. And this is for all where A bar and B bar are in the quotient ring R mod P. And this is precisely the definition of being a domain. So all these things are equivalent. Alright, how about maximal ideals? M is maximal if and only if R mod M is a field. And this sort of makes sense because you can't have anything between a maximal ideal and the entire ring, so you can't really have any quotients between the quotient by the maximal ideal and the quotient by the entire ring, which gives you 0. So anyways, by the ring isomorphism theorems, we know that the ideals in R mod M are in one-to-one correspondence with the ideals in R containing M. Correspondence being given by, well, if you take an ideal A which contains M, then you map to A mod M. M is maximal if and only if the latter of these 2 sets, i.e. the set of ideals of R containing M, is just M and R, if and only if the former set is M mod M, which is just 0, and R mod M, which is, well, R mod M. So the ideals in R mod M are precisely 0 and R mod M, and that's equivalent to R mod M being a field. Alright, so that's that. Lastly, P is primary if and only if every 0 divisor of A mod P is nilpotent. So what does it mean for P to be primary? P is primary if and only if whenever you have a product A times B which is in P, and B is not in P, then some power of A is in P. And this holds if and only if AB equals 0 mod P and B not equal to 0 mod P means that AN is equal to 0 mod P for some N. And then writing that in terms of A mod P, a bar b bar equals 0 and b bar not equal 0 means that a bar to the n equals 0 for some n. And that's if and only if every zero divisor of a mod p is nilpotent. So, right, because this is every zero divisor of a mod p is nilpotent. So here you have an so why are these two things equivalent again? So if you've got so if you've got if a bar and b bar are 0, if the product of a bar and b bar is 0 and b bar is not 0, then either okay, so obviously if this holds, then suppose you have a zero divisor. Let's call it b bar. Take b bar, multiply by a bar, and get 0. Then either a bar was equal to 0, in which case you got 0, or a bar was not equal to 0. And if a bar is not equal to 0, then a bar to the n is equal to 0. Right, and so if you take a zero divisor, what you do is you take a zero divisor a bar, and then you let b bar be another non-zero thing that you multiply it by to get 0, and then you just apply it. And then yeah. So I guess at the end there the only thing you really have to be a little careful of is that if you're going from like one of these to the others, you need to keep in mind that when you're talking about zero divisors, what you're really looking at is you're really looking at the a here, and you think of b as being chosen depending on a to be whatever zero divisor of a allows you to prove that a is a zero divisor. But yeah. Alright, the last thing here, primary decomposition. So, a proper ideal of a commutative ring is primary if and only if for any elements a and b should be product. So if the product of a and b is in Q and b is not in Q, then a to the n is in Q for some. These should be bold. For some natural number n. So that's what it means to be primary. Q is irreducible if, whenever you can write Q as an intersection of a and b, then Q is going to be one of the two things they're intersecting. And as a theorem, every ideal in the Noetherian ring is a finite intersection of irreducible ideals. And furthermore, irreducible ideals are primary. Therefore, every ideal in the Noetherian ring A is a finite intersection of primary ideals. I don't think I need to know the proof of this, but I need to be, at the very least, I need to be aware of this. And be able to use it. Like, suppose that you write this ring as an intersection of these rings. Is this a primary decomposition? Well, you just have to prove that the things that you're intersecting are primary, and then you're done. But yeah, that's about the main important things that are going to be that I'm going to be tested on in ring theory. So yeah, we'll see how that goes, and hopefully this has been useful to review if you learned anything from the ring theory section of this.